Okay. All right. So, quiz on Wednesday. It'll be based on some of the material that we're going to do today, like problem solving, and also homework 02. So, homework 02 is just basically conceptual, couple of conceptual questions, and couple of simple problems based on load line analysis that we're going to study today. So, it's not going to be that difficult. The homework itself is about 15-20 minutes long. And there's some extra credit problems in their tutorials in that homework assignment that are also about 15-20 minutes long. Again, extra credit problems are optional, but if students do the extra credit work, that extra credit will count towards your overall grade. So again, quiz 1 on Wednesday in person, and then let's start reviewing our material. 321. So let me switch. Yes, I am. Yes, recording. I know. He's gonna be asking me till the last day of fast, right? On the final itself. All right. Okay. Let me see. I think we stopped here, right? Characteristics of VI and IV characteristics. Of course, forward bias and reverse bias regions we talked about. This right here is the threshold voltage. That is a small amount of voltage that is required to turn the diode on, meaning from that point on, the diode will actually be conducting electricity or current. In the reverse side, we are connecting a negative voltage, or the cathode is at a lower potential than the anode, then it's reverse bias. Only a very small amount of saturation current would flow through. Then there's a reverse breakdown region, shows fire over there, meaning the diode could be damaged. In real life, we do have diodes that are specifically designed to work in this region. It is also known as the Zener breakdown voltage, VZ. And again, we'll look at Zener diodes later. That is the diode that is specifically operated in the reverse bias region. Okay, so the technique I wanted to talk about today is known as load line analysis. Okay, now before I talk about the load line analysis for a diode, let me just talk about load line in general. Okay, a load line in general is basically the constraints that are put on that particular device by the external circuit. So in electronics, or most electronic circuits, what are we doing? We work with AC signals, AC waveforms, right, in all sorts of shapes and sizes. More often than not, they're audio signals, right? They're audio signals. There's also television signals, mobile phone signals that we want to take and transmit either wirelessly or through wired connections, right? So when you have an audio signal, it's very, very small. Like the microphone, for instance, it's capturing the sound that I'm, the sound waves that I'm generating. And this microphone converts those sound waves into electrical signals. These electrical signals are AC, time varying, right? Depending on the tone that I use, the volume that I use, the amplitude and the frequency would change, right? Amplitude is basically the y-axis, frequency is the x-axis. So that will change. Those are going to be very, very small in size. So how do we make these signals stronger? Somebody have a question? Oh, I need to change. There you go. All right. Yes, you already reminded me. Well, one at each end, so that's good. Between the two of you, will keep me on track. So as I was saying, so we have these signals that are very, very small, right? So AC signals that are very, very small. Small and tiny. You could even use the word weak if you want. So we have weak signals and we need to make them stronger. We want to make them louder. So what do? We take these AC signals, we add them or modulate or multiply them with a stronger DC voltage or a stronger DC signal. Okay, a stronger DC signal. So imagine, if you will, you have a small AC signal like this, right? And you add them to a DC signal of this level. What do we get? Now we might have something like this. Does that make sense? It's a very simplistic representation. It's a very, very simplistic example. But the point is, you have an AC signal that's very small. You're going to add a DC, or you're going to make it stronger by providing an external DC supply of energy. Okay. So this microphone captures the sound that I'm making. It goes into the circuitry where the DC voltage would take this, and of course, very complex, of course, because we are transmitting via Bluetooth. It's going to send wirelessly over the internet and reaches the other end. But along the way, this is the kind of thing that's going to happen. So this is the input waveform. This is the external circuitry or external DC waveform. And the component that would add or modulate this AC signal would be the component that we're going to analyze using a load line analysis. Okay. So this kind of thing would happen in a transistor or an amplifier, which is something we'll look at, in later classes. Oh, I'm sorry, later in a few weeks. But for now, I just want to talk about what the load line means. So load line means we're providing an external constraint on the working of the device. Okay, so in our case, we are looking at the diode, right? We're looking at the diode. So a diode can operate depending on its value. It could operate like minus 100 volts, plus 100 volts, right? But we take an external circuit, and in this case, the external circuit is the voltage supply VSS and the resistor R. Okay, so VSS and R, the resistor R, comprise the external circuit. And this external circuit places constraints on the operation of this diode. So you cannot operate beyond these limits, which makes sense, right? I mean, if VSS is only 20 volts, this diode cannot operate beyond 20 volts, right? That just makes logical sense. But in the grand scheme of things, when we talk about amplification, that's another point to keep in mind. So the load line provides external constraints. The diode, the transistor, that component cannot operate beyond those constraints. So in simple terms, it imposes restrictions. If the noise bothers any one of you, you can close the windows. On device operation. So how do we characterize these restrictions? Well, we use load line analysis. Sorry, we use load line. It's a graphical description of these restrictions. Okay. So in this circuit, our external circuit is comprised of VSS and R. If you apply KVL around the loop, we get an equation. VSS is equal to R times ID plus VD. Right? It's a simple KVL equation. VSS is your source. A source is supplying some voltage. You have two components in the circuit, R and the diode D. Makes sense that VSS will be divided across R and the diode D, right? R voltage, VR is given by R times ID from Ohm's law. VD simply stands for diode voltage. So VSS is equal to R times ID plus VD. And that equation defines our load line. The way we find the two endpoints is basically by substituting. Now we got two unknowns, right? So to find the two endpoints of this line, the only thing we can do is by finding the value of ID and VD when the other quantity is 0, right? Because there are two unknowns, ID and VD are unknown. VSS is known because it's a voltage supply. R value will also be known because that's a resistor that we're going to choose. ID and VD are unknown. So the only way to plot it is by substituting VD or ID equal to 0, because at some point they will be 0. So those are the only two values that we can, that are known to us. So if we plug in VD as 0, we get ID as equal to VSS divided by R, right? VSS divided by R. And when we plug in ID is equal to 0, you get VSS is equal to VD. So we get one point up here, the other point up here. You join those 2 points and you get a line. That line is the load line right here. Let's take 10 seconds, think over it. Let me know if you have any questions. Does that make sense? That equation is describing the external constraints on the operation of that diode. Yes. No, we'll talk about that. Yeah. So again, that load line, depending on the values of VSS and R, can be anywhere, right? That line could be, well, let me write out here. The line could be here, or the line could be here. It could go like this. It could also go like this, right? So depending on the external circuit, depending on my application, I would design the external circuit, and using the exact same component, I can change the operation. Yes. Yes. Well, at least for this circuit. For this circuit, I mean, different circuit could be something else. Yeah. But load lines, for the most part, will always be linear, because one end would be 0, one quantity, like one voltage would be 0, the other time the current would be 0. Then when you take the load line, okay, any other questions? So when you take the load line and superimpose it over the device characteristic, you have one intersection point. The one intersection point is known as the operating point. The operating point of that device for that particular circuit. Okay, this operating point is also known as, anyone? Why is my, okay, there you go. Scroll. So this operating point is also known as the Q point. The Q stands for quiescent. And it's a word that is very commonly used in electronics. Q point or operating point stands for quiescent. Quiescent point. Name means it's lying in a dormant state, meaning we take the operating point, the device is basically fixed for operation at that point until it receives a signal. Okay, until it receives a signal. So in the case of this circuit, let's say I have my diode, right? And I have an AC signal also coming in somewhere. I'm not showing the AC signal right now, but let's say I do show you an AC signal in there, right? Let's say I'm applying it in series with VSS, let's say, superimpose on VSS on the DC voltage. AC signal is, let's say, a sinusoidal waveform, goes from like 0 to some voltage positive and then negative. What will happen? The anode is already connected to the positive terminal, right? But if I have an AC voltage and it goes to a positive peak, it's going to apply an even more positive value here. Diode will still remain on, does not really matter. My voltage, my current might increase, right? So I'm going to move up and down this load line because the voltage across the diode is now changing. And when it goes negative, if that negative signal is large enough, it might even turn the diode off. It might reverse bias the diode, which is certainly a possibility. So my negative signal goes and moves along the load line, the diode might turn off, right? Does that make sense? And so that's why the load line is of importance. We want to fix the operating point of the diode to be in the center region right here. Well, again, of course, it depends on the application. Depends on what application I'm using the diode for. Same thing is something that we'll look at again for Zener diodes and also for transistors, where it's even more important. When we talk about amplification applications, that's when a load line is even more important. Yes. No, that's not the ideal diode equation. That'll come later. I'll introduce that equation later. It's something to do with afternoon classes. Morning, it doesn't happen. Yeah, something like that. Okay, so as I was saying, load line basically is representing the external constraints that are on the component itself, on the component operation. In the case of our diode, we're looking at a simple circuit, one voltage source, one resistor, one diode. We have a simple equation where the supply voltage is split between the resistor and the diode, right? So you got VSS is ID times RD plus VD. Now, let's look at a couple of examples based on the load line. So we just call it load line analysis. And we are given in both examples, we are given the supply voltage VSS, and we're given the value of the resistor 1K and 10K. Your homework problem, there are two homework problems. They are also similar to these problems. Your quiz problems will also be very similar to these problems. So we'll look at these. You'll practice at home with the homework. You come to class on Wednesday, and then you're going to try and show me that you learned that load line analysis technique. Right? Sounds good? Easy enough? All right. All right, example 1. Let's just do 1. I was wondering why things were a little weird. Okay. First up, let's plug in VD is equal to 0. If VD is equal to 0. Now, the circuit here is the same as the previous one. Okay. I mean, if it's a different circuit, then it's a different equation, then it would be different. but both of these examples are based on the same circuit that we saw previously, which is VSS, resistor R, and then the diode D. Okay, so we plug in VD is equal to 0. What do we get? We have the equation VSS is equal to ID times RD plus VD. So ID is VSS over RD, and you get 2 milliamps. And then when ID is equal to 0, VD is equal to VSS, which is 2 volts. So you have 2 milliamps and 2 volts. I got it right on the first time. Usually I never get a straight line when I'm trying to draw. Okay. That's the resulting load line. We got 2 volts right here and 2 milliamps right here on ID. Now, if we did have a diode characteristic, we would be able to find the intersection point and find the operating point. The operating point, again, would be based on the diode characteristic, and then, of course, the external circuit. Yes. That's pretty standard, huh? For diode. It could be anything. Depends on the circuit. Are you talking in just a real life, or are you talking about like an exam or a prop quiz problem? Nothing complicated, no. I'm not gonna I'm not gonna ask you to sit there and find the Thevenin circuit and then find the. Hey. Well, in my 201 classes, you should have had plenty of practice with Thevenin and Norton. Yeah. Yep. All right, 2. Same circuit, same equation. The only difference is now the values. So let's hurry along a little bit. When VD is equal to 0, ID is VSS over R. So you get 10 volts divided by 10,000. And now you have 1 milliamp. And of course, when ID is equal to 0, VD is equal to VSS, which is equal to 10 volts. Okay. So $10 volts and 1 milliamps. Obviously, it's going like if you start at 1 milliamp, 10 volts going to be way out somewhere here, right? Almost horizontal line, very, very low slope, low value of slope. So if you want to plot this out, we can take a look. We can take a look at the diode circuitry and the constraints, and then we can plug in any value for VD. We already have 2 points, right? We already have 2 points. We already got VD as 10 volts for 0. We already have value for ID when VD is equal to 0. So now if we plot in, if we want to make the plot smaller, we can simply plug in VD is equal to 2 volts. That equation should still hold true, right? That equation should still hold true. So you plug in VD is equal to 2 volts, and you plug in the value of ID. You should be, you plug in the value of VD as 2 volts, you calculate the value of ID from there, and then you should be able to plot it on the same graph, right? Otherwise, the graph would be very, very long. So it depends on the application. In this case, if I want to plot on the same one, this is load line for 1 and load line for 2. Let's set VD is equal to 2 volts. Calculate ID from VSSR and VD. And that would come out to be, let's see, the equation. VSS VD or RD. And 8 milliamps. Sorry, 0.8. So I can then plot say this is 0.5. Let me call this as 0.8. See there, 2 tries. Load line for 2. Oh, what am I doing? That's not right. Well, but you get the idea of what I'm trying to show, right? So at 2, this is 0.8 volts. And this is load line for the second circuit. Okay, easy enough, right? As far as things go and analysis goes, rather straightforward. Yes. No, I'm just plotting on the same graph just to make a point. Yeah. It's actually too confusing to have 2 load lines on the same graph. I'm just trying to show and make a point, saying that it's the same circuit, but now we change the voltage. Resistance is the same, but just by changing VSS, you can change the load line. The operating point will also change accordingly. Yes. Right now, no. We're not. Yeah, that's later on in this class. Like, when we get to like transistor amplifiers and stuff. Yeah. Okay. Any other questions? Okay. All right. Then let's move on to a diode model. Now, the semiconductor devices, like with all things in life, there are many different kinds of models that we can use to approximate, approximate the device function, depending on the case, depending on the analysis that we want to perform. We can select which model we want to use. So one of the first models that we will look at is basically the ideal diode model. The ideal diode model, as the name suggests, uses the ideal approximation, meaning the diode does not require any voltage to turn on, meaning VD is basically 0 when it's on, or it's just slightly higher than 0. Diode gets replaced with a short circuit, When VD is less, that should be less than 0. So when the diode is reverse forward bias, it behaves like a short circuit. When the diode is reverse bias, it behaves like an open circuit. Okay. So diode is off, it's an open circuit. Diode is on, it's replaced with a short circuit. When it's a short circuit, it should be equal to 0. So it's not. Where's my pen? And this is open circuit. Forward bias and reverse bias. Again, the ideal diode model simply states that there is no threshold voltage required to actually turn on the diode. You simply apply a voltage that is slightly greater than 0 across the anode with respect to the cathode. The diode turns on. The diode is on, behaves like a short circuit. It's reverse bias. It's open. Okay, and so we get two states, two diode states, off and on. Reverse bias, it's off. Forward bias, it's considered to be on. When it's on and it's short circuit, voltage drop across it should be equal to 0. So when we analyze, yes. So when it's a short circuit, you're measuring voltage across the 2 points, so it'd be equal to 0. It should be slightly greater than 0, but for all intents and purposes, we can also say it's equal to 0. So the steps that we take to perform this analysis, well, we first have to start with an assumption. Now that assumption can be based on logic, meaning we take a look at the circuit and we can decide whether a diode is on or off. There will be a voltage, there might be a resistance in there. So we determine whether the diode is on or off. Based on the determination, we make an assumption. Now that assumption, even if it's incorrect, it does not really matter, right? We can always go back and modify that assumption. So first you assume a state, whether a diode is on or off. When it's on, you replace it with a short circuit. When it's off, you replace it with an open circuit. And then you redraw the circuit diagram. Okay, you redraw the circuit after replacing. Then you analyze using your normal circuit analysis techniques, and then you solve for the diode voltage or the diode current. This is to validate your assumption, right? This is to validate the assumption. So if the solution proves the initial assumption, then your assumption is correct. If not, it's invalid. Then you go back to step 1 and you begin your analysis all over again. So if you assume a diode state to be on, then you expect current to be flowing through the circuit, right? But if your current turns out to be 0 or non-existent or negative, that means that it's incorrect. So then you go back and you now change the assumption to diode being off. If the diode is off, the voltage across the diode should be reverse bias. If it's not reverse bias, then your assumption would be incorrect. But again, if the first assumption is incorrect, then the second one has to be correct. Both of them cannot be incorrect, right? Otherwise, well, there's an error in your problem. Make sense? Right? Yes. Well, if you're working with current, then the current should have some positive value, right? So if a diode is forward bias, it's like a short circuit. So current should be flowing through that circuit. So if we don't get a positive value, or if we get 0, then that assumption would be incorrect. And if it's off, then we would assume that current should be equal to 0. But if we get a positive number or even a negative number, then that assumption would be incorrect, because if it's off, it's an open circuit, no current should be flowing through there. Let's see. Okay. Any questions? Any other questions? In the ideal diode model? All right. So, excuse me. If given a circuit diagram with two diodes, D1 and D2, two resistors, 4K and 6K in there, and two voltage sources, 10 volts and 3 volts. Okay, we are asked to analyze the circuit using the ideal diode model. So, if we first assume D1 off and D2 on, now let's explain that assumption a little bit. I was going to straight into the analysis, but let me explain the assumption. So, D1 anode is here, cathode is here. 10 volts right here, approximately 3 volts coming here. So the assumption is no matter what the voltage drop might be, if this is on, then the anode for D1 will always be higher than the cathode, right? So you would want to assume it to be on. Okay, logically, that would be my first choice. I'm just explaining it the way the textbook problem is laid out. So I'm just going to use that for now. But logically speaking, my first thought would be that I want to have D1 on. That's what I would do. Okay. But in any case, since we are talking about the book example, I'm going to use D1 off and D2 on. So when D1 is off, you replace it with an open circuit. D2 is on, you replace with a short circuit. Now let's analyze. This is supposed to be VD1. Here we should have, since it's a short circuit, we like to calculate the current through that short circuit, right? So just look at this in isolation. You got 6 kilo ohms and 3 volts. Simple Ohm's law tells us that the current through here should be 0.5 milliamps, right? So ID2, because of the short circuit, simply given by 3 over 6,000, 0.5 milliamps. So at least that assumption is correct. It's a positive number, right? That current has a positive number, 0.5 milliamps. So my assumption that D2 is on should at least be correct. Okay, let's see. Then let's calculate VD1. If I calculate VD1, what do I get? Well, I got 10 here, and I have 3 volts here. So VD1 plus and minus, I mean voltage measured at the anode with my reference point at the cathode. This is an open circuit. My assumption is that this is an open circuit. If it's an open circuit, should have 10 volts right here. There's no current can flow through, so these 2 points are exactly the same. So 10 volts at the anode, 3 volts at the cathode. So it's plus 7 volts. Think about this. My anode is 7 volts higher than the cathode. Is my diode forward biased or reverse? If the anode is higher, meaning if the anode is at a higher potential, then the diode is forward biased. If the cathode is at a higher potential, then the diode is reverse biased. So if my anode is at plus 7 volts with respect to the cathode, my diode is reverse bias. My diode is forward bias. And if it's forward bias, then my assumption is incorrect. Yes.
You said if the anode is higher
Yes. Yep. If the anode is at a higher potential than the cathode, it is forward bias. So, last week I just talked about how we apply positive potential to the anode and negative potential to the cathode. But that positive and negative means if my anode is at a higher potential than the cathode. So when the anode is at a higher potential than the cathode, diode is forward bias. If the cathode is at a higher potential than the anode, then it is reverse bias. So in this case, my anode is plus 7 volts higher than the cathode, meaning the diode is forward bias. So if the diode is forward bias, it can no longer be open circuit. So my initial assumption is incorrect. And that is actually the purpose of the example. As I said, logically speaking, if we were trying to solve this, my first assumption would be that D1 is forward bias. So just to show you that D1 off results in an incorrect answer. Well, not incorrect answer. It results in an answer that tells me that my assumption is incorrect. Does that make sense to everyone? Hopefully. Any questions? Can everyone see why the assumption is incorrect? Sure. So we assume at the beginning that D1 is off and D2 is on. So since D1 is off, I'm going to replace it with an open circuit, right? Open circuit, meaning the voltage for D1 should show me that D1 is reverse bias, meaning the cathode should be at a higher potential than the anode. But when I complete my analysis, I determine that the anode is 7 volts higher than the cathode. So the anode is higher than the cathode, and the diode is forward bias. My initial assumption is that the diode was reverse bias. And hence my assumption is incorrect. So now I go back to the step 1 and change my assumption that D1 is not off, it is actually on. So if D1 is on, it's replaced with a short circuit. And now D2 is assumed to be off. Now you can keep D2 as on too, but that's going to be another wasted, well, not wasted, but that's going to be an extra step for analysis, which you can do, of course. But in this case, because it's a short circuit, I'm going to calculate the current flowing through the circuit. And here, because it's open, I'll calculate the voltage across it. This ID1 should result in a positive number, and this VD2 should result in a negative number. If it doesn't, then my assumption is incorrect. I have to repeat the analysis again. So let's see. So VD1 here, let me complete this right up. Be 10 minus 3 volts gives me plus 7 volts. Thus, this is forward bias and not reverse. And hence, assumption is incorrect. Okay, assumption is incorrect. Cool. Now let's analyze it for the next one. Second assumption, I'm going to say D1 on and D2 off. When D1 is on and D2 is off, I can calculate ID1. ID1 is going to be 10 divided by 10,000. You got 4 kilo ohm resistor in series with a 6 kilo ohm resistor. 10 divided by 10,000 from Ohm's law, right? Gives me 1 milliamps. 1 milliamp. Right, 1 milliamp. And now, E2, same thing on the other side. Anode for D2 is at 3 volts. Cathode for D2 is at 6 volts, right? Voltage divider. So 4 volts across here, 6 volts across here. So cathode for D2 is 6 volts, anode is at 3 volts, meaning the difference in potential is 3 volts. cathode for D2 is 3 volts higher than the anode. I will repeat the analysis when I write it down. But cathode for D2 is 3 volts higher than the anode. So let's see. So for D2, anode is at 3 volts. Cathode voltage is the same as the 6 kilo ohm resistor, right? The cathode voltage is the same as the 6 kilo ohm resistor. Does everyone see that? Right, cathode is the same as the 6 kilo ohm resistor. So if you take a look at the input side, not input, sorry, on the left side, we have a 4 kilo ohm circuit, 4 kilo ohm resistor, and a 6 kilo ohm resistor. And that point is the cathode. And diode is here. Just drawing the circuit a little bit differently. So because this is an open circuit, may as well not be connected in the circuit. 4 and 6 are in series. 10 kilo ohm resistor, 10 volts divided across 10K. You got 4 volts and 6 volts. And so this becomes 6 volts. So cathode is 3 volts or plus 3 volts higher than the anode. Hence, diode D2 is reverse bias or off. So my assumption is correct. And that's what I was trying to explain at the beginning of the problem. Logically speaking, if I look at the circuit diagram, I have 10 volts here and I have 3 volts here. So my natural inclination would be to say that this diode is on and this D2 is off. Again, so your assumption should be based on a certain logic, but even if it's not, we always go back to step 1 and rechange our assumption and redo the analysis. So if you assume a diode to be on, we expect current to be passing through, then you calculate the current. If it's a positive number, that means the assumption is valid. If you assume a diode to be off, then you calculate the voltage. And once you calculate the voltage, your cathode should be higher than the anode. Yes. No, just the load line analysis. Just the load line analysis. So you can, you can review this and let me know if you have any questions. Okay, we'll end class here for today. Wednesday, I think the first 10 minutes or so, we'll have the quiz. Again, as I said, just basic concepts and load line analysis. Do the homework. The homework is also pretty similar. 2 problems, the load line analysis, and then 2 extra credit tutorials. Then review the ideal diode model, ideal diode analysis, and then we'll look at it next class. Yes. Exponent. The E, the natural log, exponent. No, it's just exponent, right? E. Yeah, well, I'm listening.
So how I was thinking of it is that when we were doing this one, the